In today's increasingly digital world, cybersecurity is a top concern for businesses, for government entities, and for individuals. As millions upon millions of devices become connected, hackers find new vulnerabilities to exploit, and increasingly sophisticated attacks make it far more difficult for systems to identify, protect, and react to these threats. Beyond stealing intelligence or disrupting business activity, hackers now have more entry points that allow them to damage our physical world and pose serious safety risks to utilities, factories, transportation systems, and other critical infrastructures. But now, fog computing, an open architecture that is enabling innovation for IoT, 5G, and AI, has emerged as a solution for mitigating such threats. Fog's distributed architecture safeguards connected systems from cloud to device, creating an additional layer of system security in which compute, control, storage, networking, and communications work closer to the services and the data sources they serve and protect. With Fog, security resides directly in the local context, not as a remote function. Let's take a closer look. Fog nodes protect cloud-based IoT and fog-based services by performing a wide range of security functions on any number of interconnected devices, even the smallest and most resource-constrained. This includes providing a trusted distributed platform and execution environment for applications and services, managing and updating security credentials, malware detection, distributing timely software patches quickly and at scale, and more. Fog ensures trustworthy communication by detecting, invalidating, and reporting attacks. Fog can monitor the security status of nearby devices to quickly detect and isolate threats. If a security breach is detected, Fog provides trusted foundations that enable real-time incident response directly and within the local context, minimizing disruption of services. And through its scalability, modularity, capacity, and resource distribution, Fog allows for blockchain deployments to low-cost IoT endpoints. Let's look at some examples. Multiple power generators are infected with malware. Root-of-trust capabilities, based within a Fog node, allow operations managers to remotely isolate and shutter the generators that are infected, keeping service disruption to a minimum. A destruction of service attack is launched against a highly connected, multi-purpose high-rise. The building's Fog architecture ensures that the cloud is the single point of reference outside the building, greatly diminishing the attack surface. During the attack, Fog nodes continue to operate autonomously, using only their local intelligence and locally stored data to manage permissions and data accessibility for building services, ensuring that utilities, elevators, security systems, fire alarms, garage doors, and other critical services remain active. Hackers seek to take over a smart factory by targeting a vulnerability in the assembly line equipment. Fog nodes protect OT domains by monitoring traffic from the internet into the distributed Fog network and leveraging machine learning in the local context to detect a probable attack. Once detected, Fog nodes act as gateways, blocking traffic from the attackers and protecting the critical factory network. A European city utilizes a network of security cameras to comply with general data protection regulation standards. That network can anonymize video data via a local Fog node. If an incident does occur, public safety officials can disable this functionality for real-time identification purposes. At the Open Fog Consortium, security is a fundamental pillar of the Open Fog reference architecture. Our efforts are actively reducing cyber risk and turning fog-based solutions from conceptual to actionable. And now, we invite you to follow, to join this game-changing work. We are the Open Fog Consortium.